Okay, hello everybody, my name is Matsak, and today I would like to talk to you about WebRTC. So, imagine that you could add HD video or voice calling to your web app with simple JavaScript APIs. Your users don't need to install anything to use that. All calls are peer-to-peer, encrypted end-to-end with industry-standard encryption. So, is it too good to be true? Is it achievable today? Well, let's try and find out. I want you to try it right now. Go to groovio.com and enter our test code, which is test123, and let's see what happens. Let's see who's going to be first to join me. Okay, there we go. No installs, no logins, it just works. So, how exactly does it work? The technology is called WebRTC, and it stands for Real-Time Communication for the Web. It's a free and open source project hosted at webrtc.org, and the idea was initially conceived at the Google Chrome team in 2009. Google followed up with a few key acquisitions in the VoIP space and outsourced the technology in 2011. And that's when the start of the project took place. So, how simple exactly is it? Here is a snippet of code for establishing a peer-to-peer connection with WebRTC using the JavaScript APIs. On a very high level, you create a peer connection object. Then you request permissions for the user's camera and microphone using the Getusermedia API. And in the success callback of that call, you attach the media stream that you received, so basically the data from the microphone and the camera, to the peer connection object. Then you generate something that's called offer in WebRTC terminology. We'll get to it a bit later. You set it as a local description and forward it to the other peers so that the connection can take place. So, as you can see, it's quite simple. There are JavaScript objects that allow you to manipulate seemingly complex things like establishing a peer-to-peer connection. Here's a diagram of how the connection takes place. So suppose we have two devices. One is a desktop, another is mobile. And there is a peer-to-peer connection going between them. And there is some supporting infrastructure that you need to have in place. On the top, you see that there is a signaling server. And the job of the signaling is to pass messages between the peers before a peer connection is established. And at the bottom, you see that there's the stun and turn server infrastructure used for net traversal and for relaying media when a peer connection is not possible. And it's possible that in WebRTC, a connection is relayed. WebRTC is all about two APIs. The first one has to do with getting a media stream from the user's device. So basically grabbing the camera and microphone. And that API is called Getusermedia. And if the user grants permissions to access their media devices, you get a media stream object that contains one or more media stream tracks, audio or video. And the other API is RTC peer connection. That one represents a peer-to-peer connection between two browsers or two WebRTC endpoints. This object handles the bidirectional communication where the media and data can travel. So let's dive a little bit into Getusermedia. Okay, here's a simple example. And all it does is requests permissions from the user to use their microphone and camera and feeds it back to a video element on the screen. So, could be like a mirror or a loop back simple demo. So we request access to the user's media devices, and note that in the video constraint we say that we want some particular dimensions for the video. In the success callback, we locate the video element on the page and attach the media stream to that element and start the playback. And the end result is users seeing their own picture on the screen. There's also an error callback that lets us output any errors. What does the user experience look like with Getusermedia? Well, it's kind of diverse. Different browsers present different kinds of dialogues. for Getusermedia. Some browsers let you choose the devices that will be used, microphone and camera. Others simply ask you if you want to allow access to camera and microphone. Some browsers, notably Chrome, require that the page that issues the Getusermedia call is accessed via HTTPS. Others don't require that. Some of the browsers remember your permissions, some don't. So that's why there's this handy table that lists all of the differences. One important takeaway is that if you want to use Getusermedia and if you want your web application to work across the browsers, starting December last year, you need to make sure that your page is accessed via HTTPS, because Chrome will refuse to provide access to users' media devices on unencrypted HTTP. It's a security measure on their end, which we have to respect. Now, if we're getting a bit deeper into the actual parameters that you can pass to Getusermedia, one of the most important ones is constraints. It's the first object that you pass to Getusermedia, and it basically tells the engine the parameters of the audio and video streams that you want to have. And here are a few examples. The first one is very simple. Let's assume it's an audio call where you only request an audio track, so microphone access, no video access. In the second one, you want the video track and you tell the browser that you actually want the picture from the camera that's facing the user. So if we're talking a mobile device, for example, Android, browser will try to request the media stream from the front camera as opposed to the back one. In the next example, we have a limitation, actually the preferred dimensions for the video stream, and that means that the browser will try to provide us with a video feed of 1280 by 720, but even if it doesn't, the call will not fail. You might just get different dimensions for your video. And the last example is the most involved. We actually ask for a video stream of certain dimensions, but definitely not outside the specified minimum and maximum values. So quite a lot of flexibility. With Getusermedia, you can also do screen sharing. So you can get a media stream for the user's desktop or the active window. And it's actually done by specifying certain constraints. Here's an example for Chrome and for Firefox. However, there is an additional security measure that in Chrome, you need the user to install an extension to support screen sharing for your domain or your service. And in Firefox, the user needs to add the domain name of your service to a special configuration string. So quite a bit of hoops for the user to jump through, but it's all manageable. And the end result is that you can implement screen sharing with WebRTC, basically send a picture of the screen to the other user in a peer-to-peer manner. The success callback is pretty easy, so it gets called when the user grants permissions to your application to access the media devices. The important thing is that in that success callback, you get a media stream object, and it contains one or more media stream tracks, each of which is either audio or video. And you can do two primary things with a media stream object. The first one is that you can attach it to an element on the page, audio or video, to display it, to render it. And the second one is that you can attach it to a peer connection object. And what it will do, it will actually send the audio and video to the other peer, which is actually our end goal in enabling the communication with media. The error callback is even simpler. It gets called if there's any error. For example, the media device does not exist. The user does not allow us to access their camera or microphone. Or in Chrome, starting from version 47, if you attempt to call Getusermedia on a non-encrypted HTTP page, so you get an error. So back to our connection diagram, let's talk a little bit about how the actual peer-to-peer connection is made, because it's kind of a new concept of establishing a peer-to-peer connection between browsers. All of this is accomplished with the help of the RTC peer connection object, and what takes place is something that I call offer-answer dance. Everything starts with a caller, peer A, generating a so-called offer, or a session description. And a session description is basically a chunk of data that describes the media streams that this endpoint supports, the codecs, the bit rates. It actually describes the session. peer A sets it as their local description and forwards it to the other peer, which sets it as a remote description and generates something called an answer to that offer. After setting it as their local description, it bounces it back to peer A, which in turn sets it as a remote. So the end result is that both peers have their own description set as a local and the other peer's description set as a remote, and that allows the call to start. The RTC peer connection object supports the key methods required for this flow. There's the constructor that returns a new object for RTC peer connection. There's the add stream method that allows you to add a media stream that you got from Getusermedia to the peer connection object. There are the create offer, create answer methods, and set local description, set remote description to enable the flow that I talked about in the previous slide. I keep talking about this session description, so what exactly is it? A session description is basically a chunk of text in a special format, according to session description protocol, that lists the capabilities of a certain WebRTC endpoint, so your device, your browser, the codecs, the media codecs that it supports, the bit rates, additional information like the IP addresses and the ports that the endpoint is accessible with. So here's a little chunk of the SDP in action. And the important part here is that SDP is actually text format. So if you feel hacky, you can actually mangle the SDP, for example, to give more preference to a certain video codec that you like better or you think will work better in a particular environment, like a mobile network. The question is, before we establish a peer-to-peer connection between peers, how exactly do we exchange information like session descriptions between those peers? And the answer is simple, via a signaling server. Remember on the earlier diagram I showed you the signaling part? That's used exactly to enable exchange of information between peers when there's still no peer-to-peer connection. And WebRTC specification intentionally leaves out signaling out of the specification and leaves it out to the implementation. So you can use anything that comes to your mind to enable signaling. You can use WebSockets plus Socket.io, you can use HTTP long polling, you can use snail mail, post, SMS, whatever. It's up to the implementation. In Gruvia, we use WebSockets plus a custom Node.js server. So here's the place of the signaling in the overall connection diagram. So you see on top there is a signaling server, and that enables the messages to travel between peers before a peer-to-peer connection is established, or even during the call, during the session. Here's another important question. Your device might have one loopback IP. In the internal network, the IP address is different, and on the internet, it's yet a different IP address. So how does the other peer know which IP address and port number basically to knock to establish a peer-to-peer connection with you? And this is where something called ICE comes in. And ICE stands for Interactive Connectivity Establishment, and it's basically a protocol, something close to whatismyip.com for WebRTC. Stun servers, which are part of the ICE, allow the device to find out about its IP addresses and the port numbers that it's accessible. So the implication for you is that you have to have stun servers as part of your application that basically answer the question for each of the device, what is my IP address? How am I accessible to the other party? The good news is that there are quite a few free stun servers available, so you can use them, but you need to make sure that you supply those stun servers in the RTC peer connection objects constructor, because without a stun server, a peer-to-peer connection will take place only in very limited cases, like you and the other peer being on the same local network. How do the peers exchange their ICE information about their IP addresses and port numbers? Well, it's a new set of callbacks for RTC peer connection. So basically when an ICE candidate arrives, an ICE candidate is basically a pair of IP address and port number via which your device is accessible. A callback on the peer connection object is called. It's called on ICE candidate, and your job is to get that ICE candidate forwarded to the other peer, and the other peer applies it. So that's how the peers learn about each other's IP addresses on a very raw level. Now there's another issue that I mentioned earlier, and that is that no matter how hard you try, there are some peers that are just unable to establish a peer-to-peer connection to each other. It could be that there are strict firewall limitations, other factors that make it impossible for them to establish a peer-to-peer connection. And in that case, you need to make sure that the media and the data between the peers will be relayed, so routed through your server. Luckily, WebRTC supports that kind of protocol. It's called Turn, and its job is specifically to enable relaying of the media if the peer-to-peer connection cannot be established. And there are a few key considerations to deploying Turn servers. One is the bandwidth cost, because you will be paying for all the bandwidth that travels through your servers. And the other one is strategic geographic location of the Turn servers and the selection of an appropriate Turn server for a given pair of users, because you don't want two users in America having their media relayed through Australia, for example, because the latency will kill you. So Turn servers are something that you will have to take care of or opt in for a paid service, a paid hosting. On the other hand, Turn servers also double as stun. That's why stun Turn servers. And you also have to supply your Turn server addresses in the peer connection constructor. Here's the place of the stun and Turn servers on the peer connection diagram. So again, they are used for finding out of the device's IP addresses, roughly speaking, as well as for relaying the media between them in case that the peer-to-peer connection is not possible. I've been talking about audio and video very extensively during this presentation, but it's important to know that WebRTC is far from being limited just to video or voice calling. There's also something called data channels in WebRTC, and they allow you to transfer arbitrary data between peers. And you can think of it as WebSockets, just peer-to-peer. However, unlike WebSockets, there are some exciting delivery properties that you can specify on data channels. And the reason why you can do that is because the underlying protocol on WebRTC is UDP. So it's possible for you to specify reliable or partially reliable delivery in data channels, in order or out of order. So you can actually specify partially reliable out of order delivery, and that would mean that your messages are not guaranteed to arrive at the same order on the other side or to arrive at all. And the question is, why would you do that? The answer is latency. You will probably have lower latency in that case. So if it's not important for you if the messages arrive in the same sequence or if they arrive at all, you might as well opt in for this capability of data channels. On the API level, you create RTC data channel objects by calling the create data channel method of the peer connection. There are some exciting use cases out there actually for data channels, and one of them is Peer5, which is a serverless CDN, and they use the data channel technology to speed up the delivery of media assets such as video via other peers or WebRTC endpoints. I already touched on UDP a little bit, so what is comprising the WebRTC protocol stack? On the lower level, there's UDP. Then there's DTLS, and you can think of DTLS as TLS for UDP that works with the UDP protocol, and it's responsible for encrypting the streams between the peers. And one important thing here is that in WebRTC, encryption is actually mandatory. You cannot establish a non-encrypted call in WebRTC, no matter how you try. And even if the call is routed or relayed through a Turn server, it remains encrypted end-to-end. So on the Turn server, you cannot decrypt it. Then on the higher level, there's SRTP for transporting media and SCTP for transporting application data. And here's a nice diagram that shows the actual protocol stack involved. Now back to the media. What kind of codecs are actually involved in WebRTC when you're making a WebRTC video or audio call? One point here is that a WebRTC endpoint is free to implement and support any codecs that it would like. However, the standard imposes certain mandatory to implement codecs to ensure that any two WebRTC endpoints would be able to talk to each other. And if we talk about the audio codecs, there are two mandatory to implement codecs. One is Opus, the other one is G711. Opus is a free and open source one. It's actually pretty good, and it has a very good sound quality across a wide range of bit rates. So it sounds good on low bit rates, it sounds excellent on high bit rates, even better than MP3, I think. The G711 is a granddaddy of them all. It was introduced in the 1970s, and I think it's included in the WebRTC for backward support with legacy systems. With video, the situation is a bit more interesting. There are two mandatory to implement codecs. One is H.264, which is the industry standard. It's very well supported on hardware, on mobile devices. However, it's not a free codec. The other one is VP8 by Google. It's a free and open source codec, not so widely supported in hardware, but we're getting there. And again, it's free and open source. In terms of the browser support, Firefox supports both video codecs. Chrome and Opera support VP8 and now VP9, the next version, and are about to start supporting H.264 literally within maybe a month or two. So why does it really matter? It matters because when you do WebRTC on mobile, you really want your video to be compressed and played back using hardware acceleration. So it's important that the codec used by WebRTC is supported by your hardware platform. And now this one is probably one of the most important slides of the presentation. Where is it supported today? So the regular mantra is that WebRTC works today in Chrome, Firefox, and Opera on desktop and Android. And by desktop, I mean macOS, Linux, and Windows. The Android part is actually pretty interesting because not a lot of people are used to the idea that they can make a video call on Android running in Chrome or Opera, for example. But if you have a web application that uses WebRTC, it will actually run on Android, and you will be able to have a video call, a voice call, or have data transfer with data channels. Internet Explorer 10 and 11 don't support WebRTC. Safari for desktop doesn't either, but you can enable support in those browsers using a plugin. And we at Groovio use the excellent Temesis plugin for that the user has to install on their machine. And that will enable their browser with the WebRTC capabilities. Edge on Windows 10 supports a flavor of WebRTC called ORTC, Objective RTC. It's a bit different from WebRTC, and the interoperation with WebRTC is currently limited. No browser on iOS currently supports WebRTC, notably the Get User Media Call. And that means that the only way to get WebRTC running on iOS is through a native app. And the story with native apps is that you can actually take the WebRTC engine code and build it as part of your desktop or mobile application. So that's actually how we did the Groovio iOS app, by taking that code, building it for the iOS platform, and incorporating it as part of the app. So if everything fails, you always have the option of rolling out a native application. A closer look to mobile. As I mentioned, your web application that has WebRTC will work out of the box on Android, in Chrome, Firefox, and Opera. On iOS, native is the only way to go for now, although there are always rumors of Apple introducing WebRTC in the next Safari release. And you have a few options for iOS. One of them is to grab the WebRTC.org code and build it for iOS. It works. It's a bit of a headache, but it can be made to work. The downside is that the H.264 hardware support is still in the works. There's also Open WebRTC from Ericsson, which is an alternative SDK that supports H.264 hardware acceleration. And as I said, it's important if you want to save battery life and have decent performance. However, their offering doesn't seem to be as production ready at this point. And there are also third-party SDKs such as OpenTalk. You can also go native on Android, so you can build a WebRTC stack as part of your native app, Or you can take a mixed approach where you include the web view in your application, and in that web view there's a web application doing WebRTC. So what are some of the real-life challenges looking back at our experience with WebRTC? The number one challenge is that things change very fast. And just a few examples from a few months ago in December 2015, Chrome 47 came out, and you are no longer able to use Getusermedia in non-encrypted pages. There were, of course, announcements beforehand, but we developers tend to wait till the last minute. So our users who were embedding Groovio into their pages ran into some problems when they discovered that calling no longer works in Chrome. That same month, a new version of Firefox came out that stopped working with a certain old format of media constraints in one part of the API. And things like this are everyday business in WebRTC land because it's such a new technology, and you really need to keep your eye on what's going on in the community and how things are changing from browser version to browser version. And the good idea is to use a polyfill and adapter, and we use a version of Adapter.js developed by Google that kind of conceals the differences between the browser implementations from you. Also, there are services out there. A notable one is TestRTC that allow for automated testing of your WebRTC infrastructure and send you alerts when things don't work as expected. How to stay in the loop? These are some of the resources that we use to get updated of things happening at WebRTC land. There's WebRTC.org, there's the standards page for RTC peer connection. There's the Google Chrome developers channel on YouTube. This is where the WebRTC team chimes in from time to time with the updates. And there are a few blogs with excellent analysis, code snippets, and just updates on what's happening in the WebRTC world. So the question now is, given all this information, what will you do with WebRTC? And literally, today there are hundreds of exciting use cases. I wouldn't be able to cover them all, but here are some of the interesting ones. As I mentioned, Peer 5 leverages data channels to enable serverless CDN. So basically, user machines helping each other load data faster by exchanging this information peer-to-peer with each other. Telebeam allows for TV video calling, so basically making video calls to your grandma from your living room using your TV set. Zigeo does asynchronous video recording, so think a recruiting portal that allows candidates to record answers to interviews right in the portal. Taco powered group video communications for Teams, and the reason I say power because it was just acquired by Microsoft in December. Crankwheel is one-click screen sharing for enterprises. And finally, of course, there's Groovio, the world's easiest video calls, which you already got a chance to try. And to talk a bit more about Groovio, the idea is simple. You don't need to install anything. You agree with the other person on code and talk. No installs, no nonsense. We launched in 2013. It was a Flash-only version, but even back then we already had peer-to-peer. In 2014 we switched to WebRTC and never looked back. The following year we landed a venture capital investment, and there are a ton of exciting use cases using Groovio in telehealth, in real estate, in language learning, remote tutoring, etc. So that was WebRTC. Thank you very much for your attention. If you have any questions, you have my contact information. Feel free to get in touch. And if you have any questions right now, I'll be more than happy to answer.